I thought we discussed some of these issues in the class.
Oh, you did.
The one about the rotating.
Yeah.
I mean, the lowest one was around 58. That basically shows that most people did the first problem well, without any problem. Okay, so that's fine. And the second problem, some people had issues with the velocity profile. So when I say sketch the velocity profile, some didn't get it. But other than that, I was just asking to see whether you could simplify, write down the boundary conditions. Specifically, I said do not solve. And the profile must be such that I guess I may not be able to write on this one. Let me just. Okay, so you have, because it is closed, okay, and this is moving with a velocity v0, the profile must start and then decrease like this and then come back to 0. Okay, so that is the 0 baseline. Okay, and this is moving, there is no slip on both sides, but the no slip on the inner cylinder side means that it is moving with the velocity of v0 from the base. Okay, and that means towards the end it has to go like this and then return. So there will be a reverse flow. Okay, and so there will be a point where it crosses the 0 axis for the velocity profile. And half the class got it, but the other half, I guess, didn't get it quite well. And the other question, I was surprised because I thought I particularly talked about it in the class, is yeah, that's how the velocity profile should be. This problem, okay, many said that centrifugal force would throw the particle out and it will go towards the outer cylinder. Okay, and this is essentially the same problem as buoyancy. Okay, but it's called centrifugal buoyancy. In buoyancy, you have gravitational field. So if you have, okay, I guess I need to go to that. If I have a particle that is in there and G is like this, if that particle is lighter than the fluid, this is going to float up. And that is, we all understand that intuitively. Okay, when it is heavier, it is going to go down. The same idea applies when you have this that is being rotated and there is a cylinder there. Okay, so there's a sphere there. If that sphere is heavier than the fluid, okay, then the centrifugal force, the weight that is throwing it out, should be dominant compared to the pressure force. The pressure force is the integration around that, which is the cause for the buoyancy force. Now you know that as you go out in the centrifugal field that the pressure increases like this. In the hydrostatic case, it increases linearly down. And that's why you have a higher pressure down and a lower pressure up. The net pressure is upwards. Okay? And that net buoyant force always acts upwards, but if the weight is more than that, it's going to sink. If the weight is less than that, it's going to float. So in the same way, the pressure force acting on the outer part of the radius is going to be higher, but it goes as quadratic, not even as linear, quadratic. Okay, so let me ask you a question. Here, what was the rule for calculating the buoyancy force? Weight of the fluid that is displaced, right? Will that rule apply here? Zero gravity here, there's only centrifugal force. Will the centrifugal buoyant force that acts towards the inner part of the center of the axis, can you calculate it from weight of the fluid displaced? What do you think? Why? You have to integrate the pressure, right? And in this case, the pressure variation is linear, but in the centrifugal case, the pressure variation is quadratic. Okay, so you need to rederive that particular formula. But here I'm just asking you qualitatively. So qualitatively, if the particle is lighter than the fluid, then the centrifugal force it experiences outwards is going to be smaller than the pressure force that is exerted on it. And so the particle will move towards the center. Okay, and I was surprised because I thought I talked about it, but many people got that wrong. And the other one, we never talked about it, and a few people still got it right, which is good. The question is, can a velocity profile ever be like this when you have two fluids, okay, A and B, that are immiscible, so there is an interface? What are the conditions at the interface? The shear stress is continuous and the velocity is continuous. Obviously, it satisfies the velocity continuous. Is the shear stress continuous? Is the shear stress continuous in this? Why do you say so?
Because they're both acting backwards on each other, not equal.
Right, right. So there is a sign change. The gradient that you see here is opposite of the gradient there. Okay. Let me give you a different profile and see whether that would make sense. Suppose I have would that profile make sense? Is that realizable? No? You guys need to work on your physics a bit.
Maybe yes.
Why?
Because the different fluid has different properties.
Exactly, exactly. What you want obviously V1 to be equal to V2. If this is fluid 1 and this is fluid 2, the velocity is continuous. Okay, but we also want tau 1 to be equal to tau 2. That is, the shear stress exerted by this fluid on the interface must be balanced by the shear stress that is exerted by the other fluid. But the shear stress is mu1 times dv1 dy equals mu2 times dv2 dy. Okay, but mu1 and mu2 are not the same. They are two different fluids. That means that the velocity gradient doesn't have to be continuous. So you cannot insist that the velocity field be smooth like this. There will be a discontinuity in the velocity profile, the gradient of the velocity profile, because there is a discontinuity in the ratio of the viscosities. Okay, so this would be an acceptable profile. Why? Because the gradients are basically both in the same direction. Okay, so in the other one you had another interpretation which I gave in the solution is, look at it this way. If I have the maximum point, what is the shear stress at the point of maximum velocity? 0. So what is the maximum? There's a maximum in this fluid and there's a maximum in this fluid. So what does that tell you? There are two planes where the shear stress is. When the shear stress is 0, it is as if you have a free slip condition, right? It's as if the fluid is slipping past freely. So the fluid that is between these two maxima is taking a free ride. It's as if it's being pumped without any energy requirement, without any shear acting on them, because both are the shear-free surfaces. It's as if they are moving without any energy expenditure, and that's not possible either. Okay, so that we didn't discuss. So if you didn't get it, I wouldn't be that disappointed. But the other one I did. And the last problem, I think most of you got it. I guess you must have studied for problems of this type. And I did put a trick here, and some people fell for that. And the trick is, I show that the flow rate is given by this. It's exactly the same expression as the velocity profile. So this is not the flow rate. So you have to say that this is not the flow rate and get the flow rate by integrating it. Hmm?
Did that on purpose?
Yeah.
Oh, wow.
Like that. We must spend a lot of time just looking at it. I'm like, what?
And the shear stress, most people got it without any problem. And the last one, again, I just asked for a sketch of the profile, the equation and the sketch of the profile. And when you look through your exam, it should be fairly clear how I broke down the marks, okay, because I wrote down the negative marks for the points that you didn't get. So if you have any questions afterwards, feel free to come and talk to me about that. Okay. So in the last lecture, we completed the mass transfer problem from a solid to a fluid. And the main idea there was that we have a velocity that is linearly varying near that interface. So we can linearize the velocity profile. And when you do that, it becomes possible, once again, to apply the similarity transformation. But this time using the cube root of that function. And the similarity transformation transfers the PDE into an ODE, for which we can integrate and write the expression as a quadrature, as an integral that still needs to be evaluated numerically. And again, the key in all the courses is once you get the concentration profile, temperature profile, velocity profile, we are interested in calculating the fluxes, momentum flux, heat flux, or mass flux, and then the total rate. So you can expect problems of this type in the final exam. Okay, that takes you through all the three steps, like in the midterm, where you took the result all the way to the force calculation. Then we went back to fluid mechanics to look at two-dimensional flows, and there we introduced this concept of a stream function and vorticity. Stream function is a line that automatically satisfies the continuity equation, the tangent to which gives you the local velocity vector, and the distance between two streamlines is a measure of the flow rate. These are the physical attributes that you should know. Similarly, vorticity is a measure of the local angular velocity, and vorticity is a vector because you can have rotation about all the three perpendicular axes. So this is defined mathematically as omega as del cross V. Okay, and then we did a scale analysis to show under what condition we can still ignore the inertial term. That is, under low Reynolds number, the inertial term is not identically 0, but it gets multiplied by a small number, so we throw that out. And there is a large class of problems where this low Reynolds number flow is applicable. But the equation, the Navier-Stokes equation, reduces to what we call the Stokes equation. So today we are going to set up a problem of solving this Stokes equation. There are two books that are entirely devoted to the solution of this. Okay? But we are going to just look at one problem. And that problem is flow past a single isolated sphere in an infinite medium. And this is example 421 from your textbook, Versiver and Lightfoot. Now, the problem is flow past a single sphere. The coordinate system is r, theta, and then phi, spherical coordinate system. Okay. So if you take the r theta and draw this arc, that will be a semicircle, and then rotate the semicircle about the axis 2 pi radians, and you will get the surface of the sphere. So the flow is approaching this with a uniform velocity u, and our goal is to get the velocity profile near, that is, get the streamlines near the sphere, and then get the drag force that is exerted by the fluid on the particle. So the particle is fixed. We are applying a certain force on the particle to fix it. Okay. So the conditions are that it is axisymmetric, meaning there is no phi component. There are only two velocity components, Vr and V theta. That's important for you to understand in your mind. Okay. Do you understand what we mean by axisymmetry? And how do you expect the velocity profile to look like? If you take a plane passing through this axis, and that plane can be rotated 1 of 2 pi degrees, okay, 2 pi radians. So any plane will have the same velocity profile, the same streamlines. Okay, so there is no flow cutting that particular plane, and that's what this says. The phi component of the velocity is 0, and there is no variation in the phi direction. As you rotate that plane, everywhere you're going to see the same velocity. And that means you can cancel this term from the continuity equation in spherical coordinates. And you're still left with these two terms that are not 0. Okay? And remember, we'll have three unknowns. The three unknowns are Vr, v theta and P, the pressure, which is also a function of R and theta. Okay. So the continuity equation simplifies to this particular. Of course, we are assuming that the flow is steady. Okay. One can look at oscillating sphere as well, but in this particular instance, we are going to neglect that. So that is the continuity equation, and we need to find a stream function that satisfies that continuity equation automatically. Now, how do we do that? As I said in the last lecture, either you can take the definition for stream function in Cartesian frame, do a coordinate transformation, which we did at the very beginning of the class, or you can look at the book by Happel and Brunner. It's an excellent source for all the material on low-Reynolds number hydrodynamics. At the end of this appendix, he has curvilinear coordinates and he has the stream function expansions in each one of those various coordinates. Cylindrical, spherical, ellipsoidal, spheroidal. There are many, many such coordinates that he deals with. And we are just going to take the definition, and in an exam, I'll give you the definition for stream functions in any non-standard coordinate system. Now, we need to do the same thing for the Navier-Stokes equation. I don't know what that is. I think it's a picture from somewhere else. Okay. So, once again, taking the Navier-Stokes equation, we start simplifying it subject to those conditions that the flow is steady and there is no phi component. So, wherever you have phi component, you drop that out and simplify the Navier-Stokes equation. Now, in going through the solution, I'm actually giving you a little bit more information than is found in Burt-Steven-Lightfoot. But still, I expect you to fill in a lot of intermediate steps, because if I'm doing every step of the algebra, we'll be spending 4 lectures on this because it's a fairly long problem to solve. Okay. So when I say go and simplify this, you need to actually sit down after the lecture, make sure that you can cancel these terms. I know that you can do this now because you've done this in the exam, and simplify that equation to this following 2 equations, the R momentum equation and the theta momentum equation. Okay. Now the phi momentum equation will be trivial because u phi is 0 everywhere. Okay. But the R momentum equation, on the left hand side we have 0. Why? Because the flow is steady and it is low Reynolds number. So all the initial terms are not identically 0. If you go back and analyze this, for example, in the R momentum equation, you have u dot del ur. And here you have u theta divided by r, u theta squared divided by r. That's not 0. But we are going to ignore that because it is small. It gets multiplied by Reynolds number. Okay? And when you expand this u dot del, once again you will have ur, which is a function of r. It's not going to be 0. Okay? And similarly, u theta on ur, and of course this will be 0. Okay? But these 2 terms will not be 0. But we are making the assumption under creeping flow that these terms on the left hand side are 0. So this is Stokes equation, not Navier-Stokes equation. Stokes equation on the left hand side is 0. On the right hand side you will have, of course, dp dr, del square vr, and all these terms come out because of the expansion of the Laplacian in the spherical coordinate system. Okay, they are all non-zero, so we need to keep them as they are. So we can simplify 3 equations, the continuity and the 2 momentum equations, r and theta, for the 3 unknowns, vr, v theta, and p. But that is a linear equation, set of linear equations, but a messy partial differential equation. Okay, so there is a very general way of solving this, and that is explained in the book by Happel and Brunner, using something called hypergeometric functions or Green's functions. We are not going to take that route because that's a rigorous solution applicable for any shape, any arbitrary shape particle. We are looking at spherical particles, so that has certain symmetry. So we're going to impose that symmetry in the nature of the solution. That's what Burt-Steven and Lightfoot does. Okay, so we'll follow that book. Now we have the 3 equations. Any questions on that? That simplification arises simply by writing out the dependence of the velocity field. What kind of velocity field do you expect? We expect an axisymmetric 2-dimensional velocity field. The next thing is we need to write the boundary conditions, appropriate boundary conditions. One is called the far stream boundary condition. Far stream meaning far away from the sphere. Okay, so if you go back to this picture, what would be the velocity profile as you go far away from this? Far away, it's going to be simply u. Because as you go farther away, the velocity field does not feel the presence of the particle. Near it, it's going to turn around. Okay, so the velocity vector will be tangent to that. But as you go far away, the velocity field will always be pointing in the mainstream direction, u. And so you just need to state that mathematically, which says that v as r goes to infinity asymptotically for any angle theta going around the particle is u. Okay? That again, boundary conditions come from understanding the description of the problem. The boundary condition on the surface of the sphere, what are they? The classical no slip or impenetrable condition. The no slip condition says v theta at r equal to a on the surface of the sphere. The sphere radius is a. Okay? So on the surface of the sphere, the tangential component, the theta component is 0. So again, let me draw this. So v theta component would be something that is tangent to this. Vr component would be perpendicular to that. Okay? So we are saying that Vr is 0. That says the fluid doesn't penetrate into the solid because it's a solid sphere. Now, there is a variation on this, which I'll probably ask you to do in the next assignment. It should be a porous sphere. What happens if the sphere is porous? Then the fluid can flow through it. Okay? What happens if the sphere is a fluid sphere, like an oil droplet in water? What would be the boundary condition that would be appropriate? No idea? If it is a fluid sphere, does the fluid have some ability to move inside? Obviously it does, right? So think of, and it's a very common problem if you liquid extraction, for example. Okay, you have a solvent and you have droplets, and you are extracting one material from the droplets into the other medium. So you will have, if this is the velocity field, this is for a fluid, okay? The velocity field outside is going to be like this, but inside also there will be some circulation. So what kind of boundary condition would you apply at the interface? Now in this case, you will solve the Navier-Stokes equation in the inside. You will solve the Navier-Stokes equation on the outside. This problem is not very different from the problem that you had in your midterm exam, where you have two fluid. Right? So what are the conditions at the interface? Fluid interface. Velocity is continuous. Shear force is continuous. The shear stress is continuous. Right? And the normal velocity is 0, because one fluid does not penetrate into the other fluid. They are immiscible fluid. Okay? So the normal velocity is 0, the tangential velocity is continuous, and the tangential stress is continuous. So that's the condition that you would impose at a fluid-fluid interface. The tangential stress is continuous from whether you calculate from outside or inside, and the tangential velocity will be continuous. The radial velocity will be 0 for each side. So you will have two sets of the Stokes equation, one for the interior, the other one for the exterior, that you will solve. But for the solid sphere, it is 0. That means the fluid cannot penetrate into the solid. Any questions? Boundary conditions are stated from understanding the physics. So you need to make sure that you understand the physical description of the problem. Any questions? Okay. So we have posed the problem. We have simplified the Stokes equation. We have 3 equations in 3 unknowns that we need to solve. And we have stated all the boundary conditions that are appropriate for this problem. And the domain is from the surface of the sphere to infinity. Okay? In that domain, we need to solve that particular equation to get the velocities, pressures, stresses, everything that we need. Now, in spherical coordinate system, we define the stream function as follows. Now, if you notice, the stream function definition will always be like this. If I'm writing Vr, it will be in terms of the derivative of psi with respect to theta, the other coordinate. And if I'm writing V theta, it will be derivative with respect to psi r. Why is that? Because I want to satisfy the continuity equation. The continuity equation will have dVr dr and dV theta d theta. So if by doing this cross, I'll get a cross multiplication which cancels out. Okay, but I need to have these 1 over r square sine theta, 1 over r sine theta, etc. that comes out of coordinate transformation from Cartesian frame to spherical frame. So what I'm doing in this step is simply taking the definition for Vr and V theta and plugging it into the continuity equation that you see here. So for Vr, I plug in the definition. For V theta, I plug in the definition for the stream function. Okay. So this LO thing that you see, entire thing is Vr, the definition for Vr. And similarly here, the LO thing that you see here is the definition for V theta. Everything else is the continuity equation. Now you need to take the derivatives. For example, from here, sine theta, you can pull it out because you're taking only the derivative with respect to r. And then the r square and r square will cancel out. Okay, so you see that they cancel out. And what you get is simply minus 1 over sine theta, 1 over r square, d dr, d psi d theta. So here you see the cross product, d square sine, dr d theta. Similarly, in the second term, you'll also take the things that are not changing. For example, the derivative with respect to theta, so you can take r out. But of course, when you have the derivative with respect to theta, this sine theta and this sine theta cancels out. So once again, leaving you with d d theta of d psi dr. They are exactly the same term with an opposite sign. So this definition of the stream function, the defining equation for the stream function, automatically satisfies the continuity equation. Now, what are we trying to do? We are trying to solve those three equations. And the procedure that we are going to do is introduce stream function and get rid of one by one the pressures and the velocities and get a single equation for stream function by eliminating. So it's a process of eliminating the Vr and V theta and P from those three equations, the continuity and the two momentum equations. Okay, any questions? So the next step is, remember our goal is to get a single equation in terms of the stream function. So the next step is take the momentum equation, the R momentum equation and the theta momentum equation. These are equations 2 and 3 that I've just labeled here. Equation 2 is the R momentum equation. Equation 3 is the theta momentum equation. Now I'm taking the theta momentum equation, multiplying it by R to get rid of this R, and then taking the derivative with respect to R. Why? Because then I will get d square p dr d theta. And then I'm taking the derivative of this equation with respect to theta. Once again, I will get d square p dr d theta. And I subtract one from the other. Okay, so the derivative of equation 2 with respect to r minus the derivative with respect to theta of r times equation 3. That will get rid of the pressure, and you should be able to understand why that happens here. But it will not, what would it do to these terms? What will be the order of the derivative after you finish that operation? It will go up by 1 because you already have a second order term here, and you are taking the derivative one more time. So you will end up with a fairly complicated third order term, but that does not have pressure in it. So you got rid of pressure. Okay, and that will take you about a page and a half to do that derivation. And in burst river light also, they don't show all the details because once you understand the process, you can work through the remaining part. So this is the step to eliminate the pressure. To eliminate the pressure, we take equation 2 with respect to theta, r times equation 3. Sorry, with respect to r. That's a mistake there. Equation 2. Sorry, equation 2 with respect to theta. I made a mistake. It is the equation 2 is the radial momentum equation. So here I need to take the derivative with respect to theta, and here I need to take the derivative with respect to r. Okay, equation 3 is with respect to r. This is wrong. Okay, and when you do that, you get rid of pressure, and the order of the differentiation goes up to third order. Okay, and this will the pressure will cancel. Okay, but you will still have VR and V theta in that particular equation. Okay, and then what you do is you eliminate VR and V theta by using the definition for the stream function. So wherever we have VR and V theta, plug in the definition for stream function. That's another page. So about 2.5 pages of algebra, you will get the resulting equation to be this: E square psi equal to 0. Okay, I don't expect you to do this in an exam. If there's a question on this problem, I will give you the table from which you will extract this equation. So you will start working from that equation on. And in Burstover and Lightfoot, what you will see is there is a table. I hope I copied that. Yeah, there is a table, but it is inverted this way. That table gives you the equation in stream function form. After going through these processes, eliminating the pressure, introducing the stream function, and eliminating the velocities, these are the Navier-Stokes equation in terms of the stream function for the full Navier-Stokes equation. So it includes the inertial term on the left-hand side and the viscous term on the right-hand side. But for us, all we need is this viscous term, e to the power 4 psi. So fourth order equation in a single variable psi. So if I can solve for that, then I've solved the problem completely. Okay, so it's another form of the same equation, the Navier-Stokes equation in two-dimensional form, or the Stokes equation in two-dimensional form, can be reduced always into this form by introducing the stream function. So you should be familiar with this table because this has that equation in Cartesian frame. This is in Cartesian frame. This is one of them is in cylindrical, the other one is spherical. Cylindrical and spherical. Okay, so going back to this, that is the equation we need to solve. A fourth order partial differential equation, but a scalar equation. So we're dealing with 3 equations. We reduce the problem to dealing with one equation in one unknown. That unknown is psi. Okay, and the E square is an operator just like the del square. Okay, that operator is given by this. Okay, so if you have E square psi, all you need to do is put psi there, put psi there, put psi there. Okay, so it is operating on psi. Any questions on that? Okay. What have we done so far? We took the Stokes equation for a spherical geometry and imposed axis symmetry, got the 3 equations, 2 momentum and 1 continuity, and we eliminated the pressure, eliminated the velocities, and got a single equation in terms of the stream function, a fourth order equation. But we wrote down the boundary conditions in terms of VR and V theta. If you're going to solve the stream function equation, we need a boundary condition for psi, the stream function. So how do we get that? That's a mathematical manipulation because physics tells us what are the boundary conditions in terms of the natural variables, which are VR and V theta. This is a mathematical introduction. Psi is a mathematical definition through a specific equation. So we can use a transformation to find out what the boundary condition should be for psi. Okay. So the way that we are going to do this is as follows. At r equal to a, the surface of the sphere, solid surface of the sphere, we know that VR and V theta are equal to 0. But we also know the definition for VR. VR is 1 over, remember, instead of r square, I'm putting a square because it is evaluated on the surface of the sphere. Okay, sine theta, d psi d theta, evaluated at r equal to a. I want that to be equal to 0. Okay, so I want VR to be equal to 0. That means I want this entire expression to be equal to 0. Obviously, sine theta is not 0 always. A is not 0. So what I want is then this term d psi d theta to be equal to 0 at r equal to a for all theta. When can that happen? When can the derivative of a function be equal to 0 for all values of that particular variable? So if I have, for example, if I have to plot psi versus theta on the surface of the sphere, I need that to be a constant so that the derivative of psi with respect to theta is equal to 0. Okay, so that implies that psi must be equal to a constant. I don't know what constant, but some constant. Question.
Can psi be a function of r?
Psi will be a function of r. But this is evaluated at r equal to a. In general, psi is a function of r and theta, and we have this equation e square psi is equal to 0. Okay, so psi is going to change in the radial direction and in the angular direction. Just like Vr will change, just like V theta will change. But we are now talking about boundary condition, and that boundary condition is evaluated at r equal to a. So r is no longer a variable. I'm asking what is the value of the stream function on the surface of the sphere. As I go around the sphere surface, the stream function is a constant. That's what we are showing from this boundary condition. If you set the stream function to be a constant, then its derivative with respect to theta will be 0. That means Vr will be 0 on that surface. That's a way of satisfying the impenetrability condition. Okay? As we do this, you should think, how would this change if I have a fluid sphere? Okay? Any other questions on that? Now, what can you set the psi value to be? This simply says a constant. But what do we know about psi? The absolute value of psi doesn't make any sense. It's only the difference in the stream functions. If I have two streamlines, one streamline like this, another streamline like this is psi 1, that is psi 2. It's a difference in streamlines that's a measure of the flow rate. And the tangent to the streamline is a velocity vector. But the absolute value of the stream function doesn't really matter. Why doesn't it matter? We can understand this from here. I always have stream function as a derivative. So if I add a constant to the derivative, does it change anything? It doesn't, right? So I can arbitrarily set the stream function to be equal to 0. So I'm going to call this streamline as 0 streamline, as just a reference. From there, I can calculate all the other values of psi. Do you understand that? Okay. Next, the next condition is that V theta is equal to 0. But the definition for V theta is 1 over r sine theta d psi dr. But again, this is evaluated at r equal to a. Okay. So what can you say? How can you make this condition satisfied, that V theta is equal to 0? By insisting that d psi dr is equal to 0. That in fact will tell you the answer to your question, that psi is a function of r, and so there is a gradient d psi dr which is not 0, okay, in general. Okay, but in this case, if you want to make V theta is equal to 0, you should make d psi dr as equal to 0. You should impose that as a boundary condition only on the surface. As you go far away, d psi dr will be non-zero. So these are two conditions we have transformed on the surface of the sphere. We have one condition that is far away. As r goes to infinity, the v velocity goes to u. Okay, so the velocity vector can be decomposed. Now this you need to again understand the physics of it. Let's see. So if I have, this is the sphere, and I'm far away from the sphere. Okay, the velocity is u. But I'm using this velocity in spherical coordinate system. So I can decompose that into two values. What would those be? In spherical coordinates, those would be Vr and V theta. Okay, Vr would be like, this is the radial direction. I guess if that is the radial direction, I should put this as Vr. Okay, so think of this point that is away from that. Okay, so this would be Vr, and the one that is tangent to it would be V theta. Okay, and similarly, if you take a point here, you would always be pointing to the right, and you can decompose that as Vr and V theta. Okay, so Vr will be given then by u cos theta, and V theta will be given by minus u sine theta. Simply decomposing it and knowing that this is your theta, angle theta. Okay. So what we need to do is extract a boundary condition for stream function far away from the sphere as r goes to infinity. Okay. So once again, what we are going to do is use the definition. The definition for VR in terms of the stream function is minus 1 over r squared sine theta d psi dr. Notice here we are leaving this as r squared because r is going to infinity, far away. Okay. And I want this to be equal to u sine theta. I want this entire thing to be equal to u cos theta. Okay. And so I simplify this. I move the d side d theta to the left side, everything else to the right hand side. So this is not an equation. So what I'm saying here is d psi d theta must approach, asymptotically must approach u r square sine theta cos theta. Okay, so the cos theta is here, the sine theta comes from the denominator, and the r square also comes from the denominator. So the derivative of psi with respect to theta must approach this functional form, u r square sine theta cos theta. Okay, and you do the same thing with v theta. V theta is by definition 1 over r sine theta d psi dr as r goes to infinity. But I want that to be equal to minus u sine theta. That comes from the forcing of the velocity field. Okay, once again, move this to the right side, r and sine theta, so you get minus u r sine square theta. So d psi dr must be equal to that. What we want in all this analysis is to get a functional form for psi. How does psi behave as r goes to infinity for all theta? What is that? What is the nature of the stream function far away? Okay, and that's what we are trying to answer. So we know that d psi d theta must be like this, and d psi dr must be like this, far away from the sphere. So by using the chain rule, because we know that psi is a function of both r and theta, we can write this as d psi dr times dr plus d psi d theta times d theta, which simply says that stream function can change if I change r a little bit or a theta a little bit. Okay, and now I know how d psi dr changes and how d psi d theta changes. So I can take this, plug it in there, take that, plug it in there, and that's what I get, minus u r sine squared theta, which is this term, and then plus u r squared sine theta cos theta. Okay, so plug in for those, and then express them as a total derivative. That is, combine these two. Combine these two, and you can write it as a total derivative of 1/2 u r squared sine squared theta. Meaning, if you apply the chain rule and split it up, you will get these two terms. Okay. So because we have d psi equals d of 1/2 u r squared sine squared theta, psi must be equal to minus 1/2 u r squared sine squared theta. So that is the rule, that psi must approach this functional form. That's not an easy thing to see right away when you're doing it for the first time. This is why this problem, unless you work through it once, it'll not sink in. All the steps will not sink in. Okay. So we have converted all the boundary conditions in terms of the stream function. The stream function close to the boundary is psi is 0, d psi dr is 0. The boundary condition far away is psi approaches this functional form. Okay, it is still a function of r and theta far away, but it varies as r squared as r goes to infinity, and it varies as sine squared theta. It is this function that's going to give us a clue on how to construct the solution to the differential equation. Again, this is just simply given in Bursteuer and Lightfoot. The boundary conditions are this, but the steps are what I've tried to fill in here to give you an idea of how to go from point A to point B to point C, asking you to fill those point A, point B, point C path. Any questions? Okay, so what do we have now? We have this equation e square psi equal to 0, which is a partial differential equation because e square is a partial derivative operator. Subject, this is a fourth order equation, so there will be 4 integration constants when integrated. Subject to the condition psi at r equal to a for all theta is 0, d psi dr at r equal to a for all theta is 0, and psi goes as minus 1/2 u r square sine squared theta. That is the problem we need to solve. We started off with the Stokes equation, but we ended up with this partial differential equation. Now, typically what we would do, as Happel and Brenner and Sainte Kim, they do, is to use separation of variables on this, because we have two independent variables, r and theta. Psi is a function of r and theta. It is a partial differential equation. So we would use separation of variables. But the tactic that Burstiever and Light would take is the following. Because of the symmetry in the problem, because of the spherical symmetry, the function that you would typically write psi as a function of r and theta, as for example, one function which is a function of r, another function which is a function of theta. That's a separation of variable approach. But he says that let's take this function to be sine square theta. Not any general theta, because the math gets really very complicated. So let's take sine square theta. That is valid only for a sphere. If I put a cube there, that will fail. Okay? Let me ask you this question. Instead of a sphere, if I put a stone with a very arbitrary rough shape, will the equation change? The equation is the same. It's basically the Stokes equation outside of the solid shape. So I could have a rough object like this, and the fluid is flowing past it. The drag exerted on that will be different. Okay? And the governing equation is the same. Just the boundary condition will be more complicated, because I need to impose that boundary condition on such a complicated surface. But because it is a sphere, I know that from the boundary condition, that functional form, it varies as sine square far away. So I'm going to make the conjecture that it varies as sine square everywhere, near the field also. So this, in the separation of variable, I'm going to separate this as sine square theta times an unknown function r. I need to find that function. What would be my reason for doing that? If I do that and plug that into this equation, what would I get? I can take the derivative with respect to theta, because it is a known function, right? And I will have only derivative with respect to r as an unknown. So I will reduce the PDE into an ODE. Okay? So in this course, you are expected to solve only ordinary differential equations. If you have a PDE, somehow you have to find a way of converting it into an ODE. That much you should be able to do. Okay? And we have done that through similarity transformation and separation of variables. Okay? Separation of variables also allows you to convert that into a set of ODEs, in this case a single ODE. Okay, so this is a proposed solution, that it is sine square theta in theta direction and f of r. Okay, so when you take this and operate it on e square sine, you will get sine square theta times f double prime minus 2f over r squared. Okay, what am I doing here? I'm looking at, I guess maybe I should show this operation in some detail. Remember this, I'm going to substitute sine square theta times f of r into that operation that I have here. E square sine is equal to d square sine dr square plus sine theta over r square d d theta of 1 over sine theta d sine d theta. E square sine is that. Okay, now I have psi as equal to sine square theta, some function of r. So what I need to do is, wherever I have sine, I need to put this definition and take the derivative. Okay, and when you do that, what will you get? For example, in the first term, you're taking the derivative with respect to r. So sine square theta is a constant as far as that is concerned. So you will get d square f dr square. You understand that? Take this, its derivative with respect to r, second derivative with respect to r. So sine square theta can come out of it, and you'll get the second derivative, plus sine theta divided by r d d theta 1 over sine theta times d psi d theta. So here f can come out of this, right? Because you're taking only the derivative with respect to theta, right? But sine square theta will be caught inside. So you need to take the derivative of sine square theta. What will that be? 2 sine theta cos theta. Okay. So this will become 1 over sine theta times 2 sine theta cos theta. So the sine theta will cancel out. So you'll get 2 cos theta. It has to be taken again, the derivative of that. So what will that give you? Minus sine theta, right? So you'll get minus f of r 2 sine square theta, because there is one sine theta here and there is one cos. The derivative of cos theta will give you sine theta. Okay, so it's a fairly routine operation in all of them, but you need to complete. So that way you will get the sine square theta that comes out as a common factor times f double prime minus 2 f of r. I think there is an r square I missed somewhere, right? Over r square, because the r square is here. Okay, and that's what I'm showing without all these steps in here. So e square psi is simply sine square theta f double prime minus 2f over r square. Okay, that is e square, but what we want is e to the power 4. So I'm going to let f double prime minus 2f over f r square as equal to lowercase f, another function, still a function only of r, because capital F is a function only of r, its derivatives must also be function only of r. So now I apply e square one more time. Okay, so I have, this is what I need to evaluate. E square operated on psi, but I already know e square psi. Okay, and that is the sine square theta f double prime minus 2f over r square, or I can say that is equal to sine square theta times f. That lowercase f is this entire thing by definition, just defining another variable. So when I do that, substitute for that, sine square theta f of r, I'll get exactly the same operation. So sine square comes out, I have f double prime minus 2f over r square. But this is equal to 0, because e to the power 4 is equal to 0. That is the Stokes equation in stream function form. Now I'm close to getting the solution. Okay, because sine square theta is not 0, I want f double prime minus 2f over r square equal to 0. So first I need to find what is this function f from this equation. Then take that, plug it in here, and integrate one more time. Okay, so this is a second order equation, will give me 2 integration constants, which will act as a forcing term on this equation. Inhomogeneous term in that. So I can again integrate that twice, and I will get the solution for capital F, which is what I want. How many of you know how to solve this equation? This is an ODE. It's a linear ODE, but with a variable coefficient, but it's called equidimensional system. So you have something like r square, d square f, dr square minus 2f equal to 0. Typically, the ansatz is that you will say f is equal to e to the power lambda r, but in this case, you'll have to try a solution of the form f is equal to r to the power lambda. Lambda is your characteristic root. Okay, when you do that, you will get the characteristic equation like this: lambda times lambda minus 1 minus 2. The 2 comes from here. Okay, is equal to 0. And the two solutions are lambda equal to 2 and minus 1. So the solution is actually ar squared plus b over r. So it's a second order equation. There are two solutions. One is r squared, the other one is minus r to the power minus 1, or 1 over r. So a and b are the integration constants. So superposition allows you to write the general solution. Then, as I said, take that f and make it as a forcing function and set it on this f double prime. So the equation that you need to, now remember, this is the definition, right? That is f double prime minus 2f over r square is equal to f. But we found out what f is. So substitute for that and integrate one more time. Okay. So once again, because this operator on the left hand side is the same, the solution is going to be exactly the same. That is ar squared plus b over r. Instead of that, you will have cr squared plus d over r. Okay. But what happens to the right hand side, r squared and 1 over r? Those are the inhomogeneous terms. So you need to find the particular solution for that. I don't know whether you remember from your calculus, homogeneous solution and particular solution. Homogeneous solution is obtained by setting the right hand side equal to 0. then you get the particular solution for that particular forcing function. And those give you r to the power 4 and r. Now, if you are comfortable with computers, the solution to that equation can be obtained in Maple with this command. You need to understand what that command does. Dsolve is a differential equation solver. So it solves any differential equation, linear differential equation. So you see r square, derivative of f of r, but this r $2 says it's a second derivative of f of r. Okay, minus 2 f of r minus a r to the power 4 minus br equal to 0. Solve for f of r. F of r is the symbol. Then it gives you the solution like this, which is the same one that we wrote earlier. It has just factored an r out there, but it's the same solution. So after all this work, what do we have? We have the solution for the stream function, which is sine squared times this radial function, which is a polynomial, or 1 over r, r squared, r to the power 4, and r. So there are 4 integration constants that we need to evaluate from the boundary conditions. We know the boundary conditions already. Okay. So here you have to be a little bit cautious in evaluating because we have only 3 boundary conditions. What are the boundary conditions? Psi at r equal to a is 0. D psi dr at r equal to a is 0. And then the other one is psi as r goes to infinity is minus 1/2 u r squared sine squared theta. Okay, we have only 3 conditions, but we have 4 constants we need to evaluate. So what we need to do is look at this expression as r goes to infinity. What happens to the first term? It goes to infinity, but it goes to infinity as r squared. What happens to the next term? It goes to 0. So it's not giving us any trouble. So we need to keep d in there as an unknown constant. And we need to keep c as an unknown constant. We need to find that. What happens to this term? It goes as r to the power 4. That means it goes to infinity much more rapidly than we want the solution to go. How do we want the solution to go? As r squared. Because the far stream boundary condition says that the stream function should go as r squared. Do you understand the idea? Okay. So this, if you keep this function, then it will say that stream function is going as r to the power 4. That is the most rapidly growing term of all the 4 terms. So we say we cannot allow that. So we will set a is equal to 0. Okay. So we have evaluated one constant in order to comply with the far stream boundary condition. Okay. The other condition, other one is b is an unknown. But what can you say about c? Is equal to minus 1/2 u, because then it will exactly match. Why? Because this term d over r will go to 0, but br will go to infinity linearly. Do you understand that idea? That br goes linearly, r squared goes quadratically. So it's going to be the dominant term. If you compare the first term and the last term, the first term is going to be the dominant term after you've dropped out a equal to 0. Okay. So in order to match that, you can immediately say by inspection that c must equal minus 1/2 u. Then you would have satisfied the far stream condition. So by satisfying the far stream condition, you actually get the 2 constants. But remember, we did have 2 boundary conditions in the far stream. The far stream was specified as u, but we decomposed that into Vr and V theta. We really had 2 conditions for the 2 variables. The next set of constants, b and d, are evaluated at a. At r equal to a, psi is 0. At r equal to a, d psi dr is 0. Again, a lot of algebra. So you need to take the derivative of this with respect to r and then put r equal to a. Wherever you have r, put r equal to a. Okay, that's how you get a squared, a, and a. So you get 2 equations and 2 unknowns, b and d. You solve for them simultaneously. And those constants turn out to be this. So now you have actually satisfied the boundary condition, satisfied the differential equation, and the stream function. You have an analytical expression. You should be able to plot this. Okay, And when you plot this one, you will find that it looks, the streamlines look like that. Symmetric, of course. Okay. Now we have the solution. We need to trace back our path, because what are we interested in? We are interested in the pressure profile, velocity profile, stress profile, ultimately a single force. What is the drag force that they need? What is the force I need to apply to the sphere to keep it in place? If I release that, the sphere will start moving with the fluid. Okay. What is that force? That's what we want to get. Okay. So it's a fairly straightforward process because the solution has been obtained. Now I know the definition for VR, but I know what psi is. So I can substitute for psi. Take the derivative, and here I have the expression for VR. Do the same thing, and I have the expression for v theta. This is a function of r and theta, as you can notice. Okay, so I have the velocity profile in the entire domain from r equal to a to r equal to infinity. Okay, that's fairly straightforward. It still involves work because you need to take a lot of partial derivatives there. Then the work gets even more complicated because now I have VR and v theta, an analytical expression for VR and v theta. So wherever I have VR and v theta in the momentum equation in all these places, I can substitute those VR and v theta analytical expression. Take all these partial derivatives that you need to do. Okay, and when you do that, you will get an expression for dp dr. Remember, the momentum equation has dp dr and then the viscous term. Okay, so dp dr can be obtained as an analytical expression. That is the pressure variation. Sorry, the pressure gradient variation. Similarly, dp d theta. Again, there are about a couple of pages of algebra involved in taking all these partial derivatives, but Maple will help you easily because once you have the velocity profile, taking derivatives is fairly easy in Mathematica, Maple, things like that. Okay, so these two expressions give you dp dr and dp d theta. So to get actual pressure, we need to integrate that. So we're going to go and use the chain rule on pressure, which is dp dr times dr, dp d theta times d theta. So substitute for dp dr from here. Okay. And similarly substitute for dp d theta from here. Okay. And then you can express that once again as a total derivative, d of minus cos theta over r square. And because dp is equal to, these are all constants, 3 mu ua, they're all constants, times the derivative of minus cos theta over r square. So you can integrate that and you also get the pressure profile. So you got the velocity profile there and you got the pressure profile there, you have the stream function profile. You know everything about the velocity and pressure field. You have solved the problem completely. Now we need to get the stresses. Stresses particularly on the surface of the sphere. That again is not an easy task. Okay, so what is this one? Can you recognize if you see a term like that in a book or a paper? What does that represent to you? It's the area, differential surface area. Of what surface? A sphere, constant R surface. Okay, so the R here is a constant. So it is basically, if I have a sphere and I'm taking a small differential area. Okay, and so I should fix R equal to A in this one to fix it on the surface of the sphere. And then d theta would be the angle that goes like this, and phi is the angle that goes around the axis. So theta I need to span from 0 to pi, and phi 0 to 2 pi to get the complete surface area of the sphere. But I don't want the surface area of the sphere, and I know the integrated version of it. I need to evaluate the stress on that surface. Okay, so I need to know what is the normal to that surface. The normal to the surface is always in the radial direction. If I have a sphere, the normal to the surface of the sphere is always in the radial direction. That I can get in terms of the Cartesian vectors like I, j, and k. I, j, k, and r are the unit vectors in the x direction, y direction, and the z direction. what do I want? If the velocity is in the z direction, this u, I want that component of the stress in the z direction acting on the r surface. Remember, so what I'm going to have is, I'm going to have tau, for example, terms like this, tau r theta, tau r phi, tau r, things like that. Okay, all the stresses on the r surface in the theta direction, in the phi direction. But I need to take the components of them in the z direction because that's the only stress I'm interested in. Now let me ask you an intuitive question because we have done a lot of math. If I have a sphere like this and there is a flow that is uniformly approaching this, will there be a force perpendicular to that? Why? Symmetry. Okay. Now if I have the same uniform flow but I have a shape like this instead of a sphere, okay, the flow is approaching this object, will there be an upward flow? There will be. Okay, and both are have the same origin. They are due to the distribution of pressure on the surface and the distribution of shear on the surface. So you need to integrate that and find its component in the flow direction that you will call as drag. If you dot it with the normal and take the direction perpendicular to it, that you will call it as lift force, and that's what makes the planes fly. Okay, so the same mechanics that we are going to use now to calculate these forces are applied for any arbitrary shape. Okay, so what we are going to do is identify the normal to the surface, and then so Tn is the force acting on a surface with the normal n, and capital T is the total stress. That consists of the pressure and the shear stress. So if you remember from way back, T we defined as minus IP plus tau. T is the total stress that consists of the pressure, which is isotropic. That's why you have an identity matrix before that. And tau is the shear stress. Okay, so we are going to now dot it with n. N dot T, that means n dot I, n dot tau. And that's what I'm illustrating here. So that gives you the force, the direction and the magnitude of the force. This is a vector. Remember, T is a tensor. When I dot it with a vector, I get a vector. Resultant is a vector. So Tn is a vector. It's a force acting on a surface with a normal n. So I need to find out what the normal is, and that's what I'm setting myself up. Now I know what the normal is. Now if I take the normal and dot it with k, what do I get? I get the component of that force in the k direction or in the z direction. So if I take this and Tn dot k is what I need. That would be my drag force. But I need to evaluate the stress at every point on the surface and then integrate it. And that's why I need the expression for the surface integral. Okay? Any questions on that?
What is K?
K is the unit normal in the z direction. I is the unit normal in the x direction, and J is the unit normal in the y direction.
And what about that sphere you talk about? Why is not possible?
Why?
The sphere there you talk about there the force.
No, I was asking the question, will there be a force perpendicular to the flow? This is the flow direction. Okay, if that is the flow direction, I can calculate the stresses at every point and then dot it with the direction k. That will give me the component of the force in this direction. Or I can dot it with j, which will give me the component of the force in that direction. My question was, if I dot it with j, what would I get? Okay, mathematically you can show that you will get 0. Physically the argument is it is 0 because it is symmetric. Okay, so for every force that acts this way, okay, so you can decompose this force in this direction and in that direction. Okay, similarly you can decompose this force in this and in this direction. So these two forces would be additive. They will add, but these two forces will cancel each other out. Okay, so there will be no net force. But for an aerodynamic shaped object, that won't cancel out in the vertical direction. That's what gives rise to the lift force. That's called a lift force. Okay. Any other questions? Okay, so we are now ready to evaluate that force component in the Z direction. How do we do it? We take the expression for T, which I just did before. Oops. This expression, NP plus N dot tau, and I dot it with K. So N dot K and N dot tau dot K. What would be the resultant of this computation, resultant of that calculation? It's a scalar number because it is a component of the force in the Z direction. Okay, so N dot K will be a scalar, dot product, and N dot tau will be a vector, but the resultant of that with K, dotted with K, will be a scalar. And DSR is the surface area. So this is the expression for a differential, a local surface that we take. We take a point like that, this is the total stress exerted in that area. How do I calculate that? Of course, I know pressure. I've already solved for it. Okay, and do I know tau? I can calculate it because I have the velocity field. I know Vr and V theta. And tau is going to depend on derivatives of Vr and V theta. Okay, so I can calculate that. And I've already written down the expression for N in terms of ijk. And that's all I have. So I have K. K is the unit vector in the Z direction. I have an expression for N, which, where do I have it? Here. Okay. So I have figured out DSR. So I have figured out all the components that I need for this integration. N is known, K is known, tau I need to calculate. I'll show you how to do that. And then I have DSR. This is in fact the same problem that you did in one of your earlier assignments for just hydrostatics, when I asked you to calculate the force on a curved surface. You found out the normal, you found out the area, and you found out the pressure, right? Now we have, in addition, because it's a flowing system, in addition to pressure, we have the shear stress as well. So N dot K is cos theta. Why is that? Well, N is always in the radial direction. K is always pointing like this. And this is my coordinate system. This is theta. Okay, so N dot K will always be cosine of theta. Okay, so that we know. Okay, now tau, you need to go into BS Burstfield and Lightfoot to get the expression for tau. So tau has these 9 components: tau r, tau r theta, tau r phi, etc. Okay, and we need to dot that with N, but N is normal, right? In the spherical coordinate system, N can be written as simply IR0, 0. It simply says that N is always pointing in the radial direction, right? There's no component for N in the theta direction. So that's what I'm writing here, 1, 0, 0. Simply means N is pointing in the radial direction. That is dotted with this. So when you do the dot product multiplication, what will you get? You will get 1 times tau r plus 0 times this plus 0 times that, right? So that is equal to IR times tau r. That is the first component. Then you take this with the second column. You'll get I theta times tau r theta. Tau theta is multiplied by 0. This is multiplied by 0. Okay, and then the last one here comes from this. Okay, take the dot product of that with that, and that will give you I phi times tau r phi. Now this, of course, will be 0. Why will that be 0? Because of axisymmetry, right? So this will involve, for example, derivative of v phi with respect to r, which is 0, or Vr with respect to phi, which is also 0. Okay, so this will be 0 because of axisymmetry. So there are only 2 terms that are non-zero. Okay, so N dot tau dot K. Now I need to multiply, post multiply on the right side by dot K. Okay, so it's fairly a standard recipe that you need to follow. Okay, so that gives you IR tau r, which is coming from here, and then tau r theta, and then I'm now dotting with K on both sides. Of course, I'm doing the calculation in spherical coordinates. Okay, so K itself has to be expressed, that is this vector K has to be expressed in terms of IR and I theta. Okay, and that is given by this. And the handbook, the book by Happel and Brenner, the appendix, is an excellent source because you will find all these relationships between unit vectors listed there. Bert Stewart Lightfoot also has that in one of the appendices, but Happel and Brenner does a very good job of, a very exhaustive job of listing that. So the final step is take this and dot it with IR cos theta minus I theta sin theta, and that gives you this expression for n dot tau dot k, which you plug it in there. Okay, and you already know n dot k is cos theta. So going back to this expression, substitute p times n dot k, which is cos theta, and n dot tau dot k, which is this long expression, and this is the surface area, differential surface area. So you have a messy integral to do there. Okay, but before that you need to find out what is the expression for tau rr and tau r theta. Tau rr turns out to be dvr dr, which turns out to be 0 in this particular case after you substitute for vr. It's not obvious, but when you substitute the velocity profile that you have, take the derivative, evaluate it r equal to a, that will be 0. Similarly, tau r theta will be ddr v theta over r plus 1 over r dvr d theta. So plug in for vr and v theta. We already have the solution. Plug it in and evaluate it r equal to a. And that will give you this expression. Okay, and then plug them all and do the integration, and you're going to get this. F is set as 6 pi mu u a. The result, you would have seen it in undergraduate course. It was derived by Stokes. So it's called the Stokes solution, or the Stokes drag. Okay, that is a drag force exerted by the fluid on the particle. It contains two parts. The first part is coming from the pressure. So it's called the form drag. That is, there is a pressure distribution, and that gives rise to a net force. The second part is coming out from the shear. Okay, and that is called the skin drag, the viscous drag or the shear drag. So you can then define a drag coefficient. This is the definition, F divided by A divided by 1/2 rho u square. But F is your 6 pi mu u A. When you plug that in, you will get this 24 over RE. That is again a standard result that you would have seen in undergraduate fluid mechanics course. So now you know where it comes from. Actually, there is a big theory behind it. Okay, and this can be plotted as drag coefficient versus Reynolds number. So this is the result, Stokes result, which is valid up to about 0.1 Reynolds number up to this region. So this is CD over CD is equal to 24 over RE. Sorry, 24 over RE. That curve. As you increase the Reynolds number, this solution fails. Okay, and people have attempted to improve it analytically, but with very little success. But COMSOL, you can do that all the way, extend it up to here, about 1,000 or so. So beyond that, the flow will become turbulent, and even COMSOL cannot handle it.